Good evening, children. Who is there only? There are three. නම් දාන්න බලන්න. Linara connected. Linara said you have some problem on Thursdays. It's solved. මොකද්ද පන්තියක් තියෙනවද නේද Linara? If I am not mistaken. Who else is there? Good evening, Linara. And who else we have here? Kavisha. Good evening, Kavisha. Linara is there, Kavisha, and who else? Olina. Good evening, Olina. කට්ටිය මොකද කරන්නේ මේ දවස්වල? කවිෂා එහෙම යන්නේ මේපා ගෙවල් වලට වෙලා ඉන්න තත්ත්වය හොඳ නැහැ ප්‍රොෆෙසර් වෙලා ඉන්න ඕනේ මොනවද ඔලිනා ප්‍රොෆෙසර් වෙලා ඉන්න මේ සති දෙක තුන මොනවද වෙන්නේ බලන්න නේ අපිට ආයි ඔන්ලයින් ක්ලාසස් පටන් ගන්න තුනානේ නේ There are 7 now. So I see Linara, Kavisha, Olina, and who else? What the others? Oh, Piriminawai. Any boy is there? Siluni. Good evening, Siluni. තවත් ගෑනු ළමෙක් නේ ආවේ විදුන ඔන්න පිරිමි ළමයි good evening විදුන we have 1 minute more to start විදුන කොහේ යාළුවා Sachin, good evening, Sachin. Shall we start then the lesson? Uh, so before starting the lesson, I have to say you after about 2 months of normal, what do you say, normal life, we have to go back to online classes, right? Uh, the thing is, we had plans to change the gear from October after starting 2020 A-levels. Mm. We had plans and we started, of course, uh, but unfortunately, these things happen. Uh, but don't be afraid, right? So for the moment, we will do the class this way, Thursdays at 6 o'clock. Normally about 2.5 hours class. Uh, we'll see what happens. Hmm? We'll see what happens in the coming 2 3 weeks. If the things settle down and the country comes back to normal, the life, then we can start our normal classes. Then from 4 p.m. to 9 p.m. Right, the normal classes. And if we here we are doing only 2.5 hour class. If we miss some time, we'll try to catch up with after starting normal classes, right? With some extra classes. දැනට ඔයගොල්ලෝ බය වෙන්න එපා. මෙහෙම කරගෙන යමු සති දෙක තුනක්. ගිහලා බලමු මොකද වෙන්නේ කියලා. බලලා මෙහෙමම දිගටම යන්න වෙනවා වගේ පෙනුනොත් අපි තව දවසක් දාමු. හරි? දැන් පැය දෙකමාරේ තව පැය දෙකමාරේ එකක් දාමු උදේ හරි හවස හරි. Right? Free time we will for me we will start another class. If not, සති දෙක තුනක් යනකොට අපි සාමාන්‍ය පන්ති පටන් ගන්න පුළුවන් වුණොත් එතකොට ඔයගොල්ලෝ මෙහි ඇවිල්ලා extra classes දාලා තවතරම අපිට පාඩු වෙන වෙලාව කොහොමදත් ළමයි ඔයගොල්ලෝ බය වෙන්න එපා. අපේ වැඩ ටික අපි කරනවා. හරි? මේ දවස්වල යම් පාඩුවක් වුණොත් ඒක ඉදිරි කාලෙදී ඒක අල්ලනවා. අන්තිම විභාගෙ කිට්ටු වෙනකන් තියන්නේ නැහැ ඒව අල්ලන්න. අපි කොහොම හරි මොනවා හරි කරලා කවර් කරනවා. හරි? ඔයගොල්ලෝ ඒ ගැන හිතන්න එපා. දැන් මේ කරන පාඩම් කරගෙන. Right? And the other thing is we were doing integration. And of course, we were doing 2 lessons. For pure maths, we were doing integration, and for applied maths, we were doing systems of forces. Right? For the moment, I don't. I thought that it's not the best idea to continue integration online. Right? 2 problems. One is we are not at the same level at 2 classes. Integration might be වැඩි කරේ නැහැ on Thursday class, but in Sunday class we have done a little more. One problem. The other thing is it's better we do a lesson like integration here when you are here, right, physically. So I thought it's better we go to some algebra lessons for some 2, 3, or maybe 4 weeks. Like observing the situation in the country for 3-4 weeks, we'll do some algebra lessons, right? Algebra lessons is much more easy for me to do this way. බරපතල පාඩම් නම් කරා වුණා, right? බරපතල පාඩම් limits differentiation කරා online. අපි බලමු බැරි වුණොත් integration පාඩම් continue කරමු online. If not, for the moment some algebra lessons, right? You have to take your algebra book, right? This for about 3-4 weeks. About 4 weeks we'll be doing algebra online. Okay. The lesson is mathematical induction. Mathematical induction. Lesson is mathematical induction. This is some a method of proof, right? It's a method of proof. If you remember, I'm not quite sure, long ago, at the very beginning of our class, I have shown you that there are basically four methods of proof in mathematics, right? There are four methods of proof. I explained them long time ago, right? Maybe at the very first day of this class. Uh, I just have shown you that there are four methods with some examples. The four methods are number one, direct proof, right? Direct proof, which is the more familiar one for you from your O levels. In fact, all the proofs we have done for O levels, right? In geometry, maybe at other places, all the proofs you have done for O levels, right? By only by direct proof. That's the first method, right? And the second method is proof by count example. Then the third method I'll explain. Then I'll give some explanation today. Again, I'll remind them today. The third method is proof by contradiction. That's also something we have seen earlier. Proof by the second method, proof by count example. I gave some explanation at the beginning. Then proof by third method, proof by count example. We have seen that also at the beginning. And the fourth method is proof by mathematical induction, right? The fourth method is specially mentioned in your syllabus as a separate lesson, not the other three. The other three, just to give some introduction on the right. I did it earlier, but better I think I'll remind them. Very quickly remind the other three methods before coming to mathematical induction, right? There are four methods of proof in mathematics. The first is proof, the direct proof. Direct proof, as I said, this is the more familiar one for you, right? From your O levels, even the most proofs we have done the recent time in maybe differentiation, or we did some proof in vectors also recently. Proofs we have given some proofs for geometric theorems by vector methods, right? Those also by direct proof. Direct proof means you gather the data on one side, you gather the data, what's given, then you see what they prove, right? What to prove there. Here, gathering the data means that's where you are, right? And what you have to prove, on the other hand, that's your destination, right? It's like departure and the destination. Then from where you are now, from data, you construct a direct path using simplification and using theorems. You build a path directly to the result that you want, right? That's the nature of direct proof. I'll give one example just to remind you the things we have discussed earlier. Example for direct proof. Prove that x is greater than 2 implies 3x squared plus 7 is greater than 17. Some example for direct proof, right? As I said, this is very much familiar for you, this method. Answer, you are given x is greater than 2. So that implies direct proof. Direct means, yeah, here, constructing the path directly to the destination, right? X is greater than 2, that implies x squared is greater than 4. So that implies we need 3x squared. 3x squared is greater than 12. That implies you add 7. 3x squared plus 7 is greater than 19. If it is greater than 19, if this thing is greater than 19, then surely it is greater than, it has to be greater than 17, right? So if it is greater than 19, so it implies 3x squared plus 7 is greater than 17 also. So that's the proof. That's the answer. Direct proof. Yeah, better in the killing illa uttareta. That's the nature of direct proof, right? Thakala liyaganako. Four methods. This is the first method. I have explained with only an example, right? No other explanation, because in the exam they will not ask about these things, these methods of proofs, methods of proof. Uh, but you should have some idea before starting a topic. Hmm? Tagala liyagan ko. ළමයි මන් ටියුට් එකක් දැම්මා ඔයගොල්ලෝ අතින් ලියාගත්තත් කමන්නේ print කරගත්තත් කමන්නේ ඔයගොල්ලෝ දැක්කා නේද ඒක ලියා ගන්න හරි ඇතිනේ කවිෂා ඔලිනා දැක්කද විදුන හරි ඒක මේ අඩු ගානේ අතින් හරි ලියා ගන්න ඕනේ හරි නේද ළමයි shall we go to the second method second method is second method of proof is proof by count example. Proof by count example. Right. Proof by count example. Second method. It is used in a special situation. Count examples you use when you don't agree with a given statement. Right. In fact, it is not to prove. Count example method is used to disprove something that you don't agree. Right. Given some statement, you don't like to want to accept it, so you want to prove that it is wrong, it is false. So sometimes you can use count example method, right? For instance, අපි තුමු කවුරු හරි කියනවා කවුරු හරි කියන්නේ කියලා තියෙනවානේ රොබර්ට් නොක්ස් කියලා දෙන්නේ ලංකාවේ ඉන්න මොනවද කියන්නේ සිංහලයේ ඔක්කොම බොරුකාරයෝ. එහෙම කියලා තියෙනවා රොබර්ට් නොක්ස්. හරිද? සිංහලයේ ඔක්කොම බොරුකාරයෝ. රොබර්ට් නොක්ස්ගේ ප්‍රකාශය. Statement. Signal if you don't say like to accept it, right, as a true statement, if you wish to prove that Robert Knox is wrong, that statement is wrong, what do we do? So you want to prove that Robert Knox is wrong, right? මම ඇත්තද බොරුද කියලා රොබර්ට් නොක්ස් කියපු එක කොහොමද අපි හිතමු අපි පිළිගන්න කැමති නෑ කියලා. එහෙනම් අපි මොකද කරන්නේ? Robert Knox වැරදි කියලා පෙන්නන්න. His statement is wrong. If you want to show that his statement is false, what should you do? ලංකාවේ ඉන්න ඔක්කොම සිංහල මිනිස්සු ගෙනලා පරීක්ෂා කරලා බලන්න ඕනද බොරුවක් කියපු නැති මිනිහෙක් ජීවිතේට මේ ඉන්නවද කියලා. අඩු ගානේ පොඩි බොරු කියවත් ගානේ ලොකු බොරු කියපු නැති මිනිස්සෙක් හොයාගන්න පුළුවන්ද කියලා ලංකාවේ ඔක්කොම සිංහල මිනිස්සු ගෙනලා චෙක් කරන්න ඕනද? එහෙම නැත්නම් අපිට එක සිංහල මිනිස්සෙක් ඉදිරිපත් කරන්න පුළුවන් වුණා නම් I gave the tut earlier means with my message I have like posted in the group, right? Some 3-4 days before, not today, some 3-4 days before, maybe not 3-4, last Monday, Tuesday, and asking you to copy it or to have a printout of it, right? Function tut to you also. That was for 2022. එහෙනම් මම මේක දාන්නම් අද දාන්නම් ළමයි. මම තව ටිකකින්ම දාන්නම්, right? මොනවාද? Proof by mathematical induction. මම ඒක දාන්නම්. සිංහල මීඩියම් කට්ටියට දාලා තියෙන ඉංග්‍රීසි මීඩියම් එකට. එහෙනම් දානකොට වරදින්නේ නැති. ෆන්ක්ෂන් ටියුට් එක ඕනේ නැහැ. ඔයගොල්ලෝ ළඟ තියෙනවනේ. Okay. I'll give it today, right? Very sorry. By mistake. Right. So then අපිට රොබර්ට් නොක්ස්ගේ statement එක වැරදි කියලා පෙන්නන්න ඕන. If you want to prove that he's wrong, so it's sufficient you find one person, one Sinhalese person. ඒක හරි අමාරු වෙන්න පුළුවන්. Say you can accidentally find some Sinhalese person who hasn't lied for the lifetime. බොරු කියපු නැති සිංහල මිනිස්සෙක් හොයලා පෙන්නන්න පුළුවන් නම් ඔන්න එක්කෙනෙක් පෙන්වුවා මේක. ඔක්කොම මිනිස්සු ගෙනල්ලා පෙන්නන්න ඕනේ නැහැ. එහෙම පෙන්නන්න පුළුවන් නම් මම දන්නේ නැහැ පුළුවන්ද කියලා. පුළුවන් වුණොත් ඔන්න අපිට කියන්න පුළුවන් රොබර්ට් නොක්ස් වැරදි කියලා. So that is a counter example. That single person. If you can find and produce a single person who hasn't lied, Sinhalese and lied for the lifetime, so that's a counter example. That's a counter example against the Robert Knox statement. And for example, like the Magina, looking now from Kabro, Kalupate. All the clothes are black. That's my statement. If you don't agree with me, do you have to collect, go and get all the clothes in the world and check one by one? Looking, if you don't agree with me, and if you wish to prove that my statement is wrong, right? So do you have to get all the clothes in the world, or is it sufficient? somehow, if you can find one row which is not black, is that sufficient to produce one row which is not black to disprove my statement? Right? It's against my statement. So that is a counterexample. That single row which is not black. Okay, that's the counterexample method, right? We use counterexample method to disprove statements. Example, if I say, so I'm saying x is greater than 3 is greater than implies x square is greater than 10. Is this true? Do you agree this? Do you agree? කියවලා බලලා හිතලා බලලා තීරණය කරන්න ඕන පිළිගන්නවද නැද්ද කියලා. එහෙම නැතුව අර කාලාම සූත්‍රයේ බුදුහාඳුරු කියලා තින්නේ නේ. ගුරුවරු කිව්ව පළියට අම්මලාතා කිව්ව පළියට මොනවද පූජක පක්ෂය කිව්ව පූජ්‍ය පක්ෂය කිව්ව පළියට පිළිගන්න එපා. විමසා බලලා තමයි පිළිගන්න ඕනේ. මොකද කියන්නේ? Do you agree? Do you accept this? සිලුනි විදුන ඉන්නවා. තව ඉන්නේ කවුද? සචින් පිරිමි ළමයි. කවිෂා, do you agree with my statement? Yes or no? Simply. Sachin says no. Litmal agrees with me. What about the others? Litmal, then we that. What about the others? Agree or not? Litmal, change mind. No, ikaw තමයි Robert Knopf කිව්වේ නේ. Okay. What about the others? What's the answer? Agree or not? Yes or no? Two answers saying no, Sachin and Vipmal. අනිත් අය මොකද කියන්නේ? බොරුවට හරි උත්තරයක් කියන්න එපා. Vipmal answers taken back. No, saying Dinara. So my statement is whenever x is greater than 3, then x square has to be greater than 10. That's my statement. Whenever x is greater than 3, then x square is greater than 10. That's my statement. If you don't agree with my statement, so you have to disprove. You have to prove that it is wrong. So your answer is no. No. Prove. To prove that it is wrong, you have to give the best way to disprove this is to give a counterexample. Do you have some counterexample against my statement? Any example? Counterexample? Yes, Sachin, Dinara. If you don't agree with me, yeah, take. Sachin says taking 3.1. Okay, let x be equal to 3.1. The counterexample, right? Then definitely x is greater than 3. And x is greater than 3, definitely. But what about x squared? X squared is 3.1 squared. 3.1 squared is 9.61, isn't it? 9.61. This is not greater than 10. It is less than 10. In fact, less than or equal to 10. Hmm? Yeah, it is. Yeah, it is less than 10. So that's sufficient. X is greater than 3, but x square is less than or equal to 10. So this is a count example and proof of that this statement is false, right? Uh, this is a count example. The count example. Okay, so that's the example. Just to remind you, the count example method. Okay, ලියා ගන්න පුළුවන් එකක් දාලා. මම මේ note එකක් දෙනවට වඩා පොඩි මතක් කිරීමක් කරන්නේ. මට මේ ටික නැතුවත් කෙලින්ම මේ පාඩම පටන් ගන්න තිබුණා. එහෙම නම් ඔයගොල්ලන්ට වැඩි අදහසක් එන්නේ නැහැ. මම ඒකයි මේ ඉක්මනින් මේ ටික මතක් කරගන්න යන්න හැදුවේ. ඉක්මනින් ලියා ගන්න. Yeah, the answer is correct, right? Sachin? Olina? Yes, Olina gave the same. Okay. Can I go to the next? Then the third method. Method 3 is proved by contradiction. Contradiction method. Proved by contradiction is the third method. Do you remember at the beginning, very beginning, we have seen this, we discussed this in detail because we used it especially in real numbers. Do you remember to prove that square root of 2 is irrational? In that proof, we use proof by contradiction method, and I explained it then there with more examples and details, right? Today I am going to explain it again But I'll give one example just to remind you. Uh, the example, count example, contradiction method is seen with the example. Example, prove that x equals 1 is not a root of say 2x squared minus 3x plus 7 equals 0. So you have to prove that x equals 1 is not a root of this, right? Proof or answer. By contradiction method. Do you remember when you use the contradiction method? So how do we start? To start it, what do we write? We want to show that x equals 1 is not a root of this. So how do we start? Remember, when we use the contradiction method, anybody remember how do we start in this example? Abhita says x equals 1. Sachin says factors. Abhita, incomplete. Assume that x equals 1. Yeah, saying Linara, x equals 1 is, assume or suppose that x equals 1 is a root. You have to prove that x equals 1 is not a root. We start by the total opposite of that, opposite of what we have to prove. That's what we do in contradiction method, right? Remember, in contradiction method, we start by supposing the total opposite of what we have to prove. Yeah, suppose that x equals 1 is the root of 2x squared minus 3x plus 7 equals 0. So if so, x equals 1 should satisfy this. So let's substitute x equals 1 is this in this, substituting you get 2 into 1 minus 3 into 1 plus 7 equals 0. This gives 6 equals 0. If you start by supposing that x equals 1 is a root of this quadratic equation, then at some stage you get that 6 equals 0. Will anybody agree this? Nobody will accept this. So you call this, this what we call. So here we came to a contradiction, right? This is the contradiction. So this is a contradiction. This is a contradiction. This is a contradiction. Then we turn back and check why we got a contradiction, right? What's the reason that we got a contradiction? We came to a contradiction. When you check, go back and check, we see only 2-3 lines before away, you see that it's the supposition, right? It's our supposition that x equals 1 is the root. This supposition led us to this contradiction, 6 equals 0. So this is the reason which gave this contradiction. Now we correct it, right? Now we correct it. Correction is x equal 1 is not a root, right? Therefore, finally, conclusion, x equals 1 is not a root. So that's the contradiction method. Hari, unman kota mata kara example legi. Ikpante liya lamai. Now then we can start our lesson, right? Our topic is the fourth method, proved by uh, mathematical induction. Okay. Now you can go to the fourth method. Method 4 is our topic. Right. Fourth method is proved by mathematical induction. Proved by mathematical induction. Proved by mathematical induction mathematical induction. We say mathematical induction because the term induction you need at other places also. Remember in the physics class, magnetic induction, electric induction, things. Now to identify this separately in mathematics, we say this is mathematical induction. Okay. So mathematical induction. So what is this? Where do we apply it? So in previous example, in the examples we have taken earlier for the three methods, so we have seen that there are occasions where we apply those methods. When to decide, uh, when to decide to apply proof by count example, right? Sometimes when to apply direct proof, when to apply proof by contradiction. You read the question, so you get some idea. The thing you have to prove, you should have some idea. This is the best way to select the proof, method of proof, right? For the given task. Similarly, at what occasions we apply proof by induction. So, what are the situations in which we apply proof by induction? Right? It's a special case, a special situation when where we decide to select proof by induction. So, what is it? Proof by induction is used in proofs. If you have to prove something true for all integers, some statement you are going to prove it is true for all integers starting from some starting value, right? Some integer. So some statement that n, the statement of n, you have to prove true for all integers, say starting from 1, 2, 3, 4, 5, 6, and so on. That is, you have to prove that the statement is true for n equals 1. You have to prove that the statement is true for n equals 2. It is true for n equals 3, and so on, right? Or maybe not starting from 1. It can start from any other positive integer. Maybe 4, 2, 3, 4, 5, starting from 2, right? In a case like this, for instance, take some statement like this: x to the power n minus a to the power n is divisible by x minus a. Divisible by x minus a for all n equals 1, 2, 3, 4, all the positive integers starting from 1. This is a statement given, right? X to the power n minus a to the power n, where n is any positive integer starting from 1 is divisible by x minus a. Some example. So if you have to prove something like this, uh, this thing, of course, a simple example, right? This, of course, you can prove by direct method also, but usually, in a case like this, to prove that it is true for 1, 2, 3, 4, 5, 6, the best option is usually the best option is to go for induction, mathematical induction. Another example, you are asked to prove that 7 to the power n minus n. The n to the power 7 minus n is divisible by 7. This is the statement I made, right? N to the power 7 minus n is divisible by 7 for all n equals 1, 2, 3, 4, and so on. So you have to prove this. But what if you try to, for a statement like this, definitely it is this method, right? Proof by induction. For this, of course, you can apply a direct proof also. But for this is the best option, proof by induction. if you try to prove it by say some say like direct method, you can prove that it is true for. You can try to show that it is true for n equals 1. What do you think? N equals 1. If n equals 1, that will be 1 minus 1, 0. This is equal to 0. 0 is divisible by anything, right? Other than 0. You can divide 0 by anything other than 0. So this is divisible by 7 for n equals 1. So this statement is true for n equals 1. What if n equals 2? N equals 2, you get 2 to the power 7. 2 to the power 7 is 128, isn't it? 128 minus 2, 126. 126 is divisible by 7. It is, yeah, divisible by 7. So this is true for n equals 2 also. Then you have to, you try say to prove that it is true for n equals 3, n equals 4. Okay, karang pula meda jalan. Taking one by one and prove one at a time and prove for positive integers. එහෙම මේකේ proof එක ලියන්න ගත්තොත් ඔයගොල්ලෝ මේ ආකාරයෙන් නකන් ලිව්වත් මේ ඉවරයක් වෙන්නේ නැහැ. ඉවර කරන්න බෑනේ, right? So that's not the way of proving this. To try to prove that it is true for n equals 1, then for n equals 2, then for n equals 3. So it will be an endless process. Okay, so to prove something like that, something like this statement, our method is by induction. So what is this method? Proof by induction. In proof by induction, this is what we do. Now everybody listen carefully. Now I am explaining the proof by induction, the principle or the theory or the concept behind this method, right? Listen carefully. Our method is this. For example, say you have to prove that statement, this statement Fn is true for all positive integers starting from 1, that is 1, 2, 3, 4, 5, 6 and so on. We have to prove that this is true for all positive integers starting from 1. For instance, what we do in this method is you show that it is true for the very first integer, starting integer. In step 1, prove that the statement, this is the statement, this is the statement, let's name it A, prove that A is true for n equals 1. So that's the first step. Right, you prove it there. So usually this step is very, very easy. Substitute n equals 1 and show that it holds, right? Then keep it aside for a while, right? You just prove that it is true for 1, n equals 1, then keep it aside. Then what we do is step the next step, step 2 and step 3. Then what we do is then we prove that if the statement is true for any n equals p, if A is true for some positive integer, some n equals p, a positive integer, right? If this statement is true for some positive integer p or whatever you take, right? For the moment I'll take p. If this statement is true for some positive integer p, we prove that then it is true for, it has to be true for n equals p plus 1 also, right? So that's the heart of this proof. What we do is we show that if the statement is true for some positive integer p, then it has to be true for n equals p plus 1 also, right? So this is the main thing in the proof. If true for n, the statement is true for P, then it has to be true for n equals P plus 1 also. So in other words, you start by supposing that the statement is true for some n equals P. You suppose that it is true for n equals P, then use this to prove that it is true for n equals P plus 1. Now we have if true for P, then true for P plus 1 also. Right? If true for n equals P, then true for n equals P plus 1 also. We have this in our hands. And when you go back to the first step, at the very beginning, we have proven that it is true for n equals 1. At the beginning, we have proven that it is true for n equals 1. Now you have proven that if it is true for any p, then it has to be true for p plus 1 also. So we have two things. If true for p, then true for p plus 1 also. And now you have true for n equals 1 also. Now connect them together. What do you get? If you connect them together, what do you get? This says if true for any p, then it should true for n p plus 1 also. And again we say it is true for n equals 1. Connecting them, what is the result you get? Kian balan, මොකද වෙන්නේ? When you connect those two statements together, what is the immediate result? A very simple question I am asking. What do you get combining these two together? මොකද කියන්නේ ඔලීනා? ඉස්මාල් මොකද කියන්නේ? ඔය දෙක එකට තියලා බැලුවම මොකක්ද අපිට ලැබෙන්නේ? What is the immediate result that we get? This is a very beautiful argument in mathematics, right? Proved by induction. Very beautiful argument. Combining these two, what do you get? Immediate result is it is true for 2. Yeah, Lipman. It is correct. Here we say if it is true for any p, then it has to be true for p plus 1 also. Now we say it is true for 1. We have this in our hands, true for 1. Then from this you can say it has to be true for 2 also. If true for 1, then it has to be true for the immediate next positive integer. If true for some positive integer, then it has to be true for the immediate successor, next positive integer. If you have that it is true for 1, then from this you get it has to be true for 2 also. Now if true for 2, now what happens? From this you get that it is true for 2. Then from that, if true for 2, now what happens? Again by this step, you can say if true for 2, now what do you say? We have shown that it is true for 1. That by this argument, we get then it has to be true for 2. If it is true for 2, then again by the argument, you get what is it? Here, Balan. Now, if it is true for 2, then we get it is true for 3 also. Then if true for 3, again by the same argument, you get it has to be true for 4. Then from that you get it is true for 5. You can chain එකක් වගේ යනවා. We have just proven that it is true for 1. Yes, yes. Correctly, Nara. We just have proven that it is true for 1. Then by this argument, if true for 1, it has to be true for 2. If true for 2, then it has to be true for 3. If true for 3, then it has to be true for 4. So we just chain it up again for up to infinity, all the positive integers, right? So we have proven the statement. It's done. That's all you have to do, right? To show that it's true for all positive integers n. So that's the method of proof by, that's the principle behind proof by induction. I'll explain with some examples. For the moment, you got some idea, children? What again? ඉන්න කට්ටියට තේරෙනවද ඔය කියපු දේ? අභීත විදුන මොකද කියන්නේ? කවිෂා ඔලීනා ඉන්නවා මොකද කියන්නේ? Argument එක තේරුණාද? It's a very beautiful argument in mathematics, right? Pure mathematics. You got some idea. That's all I need for the moment, because things will be much more clear with one or two examples. Kavisha says yes. What about the others? Yes, Abhita? Okay, thank you. Now we can go to examples. You don't need to write any note, right? You don't need notes. We'll explain things with examples. If you got some idea of what I have explained here, no need of writing notes. We can directly go to the first example. ගොඩක් ලස්සන ලස්සන දේවල් අපි ඔප්පු කරලා පෙන්නනවා මේ මෙතඩ් එකෙන්. හරි. දැන් මේ ගන්න එක්සැම්පල්ස් පළවෙනි එක දෙකම ගන්න. හරි ලස්සන දේවල්. Example 1, I'll take the same examples that I have taken earlier. Now we will take them more formally. Prove that x to the power n minus a to the power n is divisible by x minus a for all n belongs in for all positive integers. Okay, ලියා ගන්නකො. ඊට පස්සේ අපි answer එක ලියමු, proof එක ලියමු. දැන් ලියා ගන්නම මට මේ මුළු board එකම ඕනේ වෙයි. Just take it down. Proof method 4, proof by mathematical induction. The first example, prove that x to the power n minus a to the power n is divisible by x minus a for all n belongs n. Okay, so let's see the answer. ලියාගත්ත නේද ළමයි? පළවෙනි example එක හැමෝම ප්‍රවේශමෙන් බලා ගන්න. right? Answer on the proof by induction, by mathematical induction. Of proof of x to the power n minus a to the power n is divisible by x minus a. So this is the task, to prove that xn minus a n is divisible by a. So as we said earlier, our step 1 is to prove that this is true for n equals 1. That's first step. When n equals 1, do you see that x to the power n minus a to the power n. So we have to show that this statement is true for n equals 1. That's the first step. That this is true for, this is divisible by x minus a when n equals 1. That's the task, right? So when n equals 1, you get this is equal to x to the power 1 minus a to the power 1. That is x minus a. This is equal to x minus a. So nothing to say. Very clear. It's seeing that this is divisible by x minus a itself. So this statement is, you can show that very easily. It's always very easy, right? The first step. Very easily we see that this statement is true for n equals 1, right? Always in these proofs, the first step is very easy, and you get 5 marks for writing that. This is divisible by x minus a. So that implies a is, this statement a is true for n equals 1. So first step is done, right? Then second step, we just assume that this statement is true for n equals some p, a positive integer p, right? When n equals p, some positive integer, suppose that a is true for n equals p, some positive integer. That means we are assuming that this is divisible by x minus a, when n equals p. So that implies, that gives when you replace n by p, x to the power p, n by p, you get x to the power p minus a to the power p. You get that this is divisible by x minus a. Divisible means when you divide it by x minus a, division algorithm, when you divide by x minus a, you get some quotient, say gx, some quotient but no remainder. Some quotient but no remainder. So that's when you say it's divisible, right? So this is equal to x minus a into some gx. If you assume that this statement is true for some n equals p, then you get that x to the power p minus a to the power p is equal to x minus a times some gx, the polynomial, right? For some polynomial or quotient polynomial gx. That's the assumption, right? Now the third step. This is also very easy, always very easy. The second step, assumption. Assumption එකක් ලියන්න බැරිය. ඕන දෙයක් suppose that කියලා අපිට ඕන දෙයක් නිකන් ලියලා දාන්න පුළුවන්, හිතා ගන්නත් පුළුවන්. And you get writing 5 marks for just writing this, right? All first step is always very easy. Second step is also very easy. In this proof, now when n equals p plus 1. So this is the real task in this method of proof. This is the real task. So you have to show that this statement is true for n equals p plus 1, or this is when n equals p plus 1, this is divisible by x minus a. So that is the task, and that proof we do using this upon this. We say if it is true for n equals p, then it has to be true for n equals p plus 1. So this is the main tool that we have, this assumption. Using this, or upon this, you prove that it is true for n equals p plus 1. So what should you keep in mind? That in this proof, somewhere, this is the main tool that you have. Somewhere, somehow, you have to connect this with this step. Okay. So if any when n is equal to when n is equal to p plus 1, so you get that that left hand side xn minus a is equal to x to the power p plus 1 minus a to the power p plus 1. X to the power p plus 1 minus a to the power p plus 1. Now we have to show that this is divisible by x minus a, and that proof we do mainly using this. That means we have to connect this here. So how to connect it there? We have to get some use of this definitely, right? That's the main thing. That's the key point. So how to connect it there? So when n equals p plus 1, xn minus an is equal to x to the power p plus 1 minus a to the power p plus 1. So somehow we have to connect this there, right? So if you want to see this here in mathematics, what we do is we don't waste our time just to write down it there, right? Just write down it there. If you want to see x to the power p minus a to the power p here, right? We just write it there, right? And then you have to balance. You have written these two are equal. Now you have to make them equal, right? For the moment they are not equal. You have to make them equal. When you make them equal, first mainly consider the more complicated. First equate the more complicated terms, right? Here of course it is x to the power p plus 1. Just equate them to make x terms equal. It's very easy. Just take a factor x out. Just write x there. Then once you write this here, to make x terms equal, we just write an x here. Now x terms are balanced, but look at this. You get minus x a to the power p. Here, in addition to the x terms are okay now. X to the power p plus 1 is there, but here you get minus x a to the power p. This is unwanted, right? This is unwanted. So if unwanted, you have to get rid of that. So it's very easy to get rid of that. To get rid of that term, to get rid of this unwanted term, we just add it plus x times a to the power p. Okay, so this unwanted term disappears, but further we need this minus a to the power p plus 1. We need that to appear here. So just write it. Just write this term minus a to the power p plus 1. Now two sides are equal. Okay, we have what we wanted here, and further two sides are equal, right? ඔක තේරුණාද ළමයි? ඔය කරපු දේ මොකද කියන්නේ ලිත්මල් සකින් ඔය ස්ටෙප් එක තේරුණාද? ඕක තමයි key point එක. මෙන්න මේක ගෙනියලා කොහොම හරි අතන හොඳ සිංහලෙන් කියනවා නම් ඔබා ගන්න ඕනේ එතන. දැන් ඒක තමයි මම කරලා පෙන්නුවේ. ඒක තේරුණාද ඒ ස්ටෙප් එක? ඕක කරා නම් ගානිතු ටික හදලා එක බොහොම ලේසි. You got that? මොකද කියන්නේ ළමයි? අකපු දෙය තේරුණාද? අපිට ඕන කරන එක ගෙනල්ලා මෙතනට සම්බන්ධ කරගන්න හැටි. And then balance two sides. Is that clear? Or you want me to explain it again? ලොකු බරපතල දෙයක් කරෙත් නැහැ. මොකද කියන්නේ ළමයි? විනාලා විනාලා රිත්මල් තේරුණා කියනවා. අනිත් අය මොකද කියන්නේ? ඔලිනා මොකද කියන්නේ? කියපු කාරණේ පැහැදිලිද? නැත්තම් නෑ කියන්නේ. ඔව් නම් ඔව් කියන්නේ. මොකද කියන්නේ ළමයි? අනිත් අය තේරුණා නැද්ද ඒක? මම ඕනනම් ආයෙ ලියන්නම් මෙතන. What I did was, I write it here. X to the power p plus 1 minus a to the power p plus 1. This is what I had. This is what I had. X to the power p plus 1 minus a to the power p plus 1 when n equals p plus 1. And I wanted to see this thing there because I want to get some use of this. So I just wrote it. X to the power p minus a to the power p. That's what I need. I just wrote it. Then to balance x terms. To balance x terms, I just wrote x here. Wrote x here. Now, multiplying these two, x terms are balanced, right? You get x to the power p plus 1. Writing x here, we make x terms equal. But here you get some minus x into a to the power p. This term we don't have here, right? This term is unwanted. When you make them equal, this term is unwanted. I just, to get rid of that, I just added that. X into a to the power p. Now these two will cancel. It's like it is not there now. For the moment we have them, when these two get cancelled, we have x to the power p plus 1 only. This is there. You need this further. So for that, we just write it there. Now, once these two terms get cancelled, you get two sides are the same. Now, two sides are equal. That's what we did, right? අපිට ඕන කරන එක ලිව්වා. ඊට පස්සේ අඩුපාඩු හදලා බැලන්ස් කරලා දෙන්න. හැමතිස්සෙම අපිට ඕන කරන එක මෙතන ලියා ගන්න ඕනේ. දැන් තේරෙනවද ළමයි? I wrote it in one line. දැන් වැඩිපුර තේරෙනවා මෙතනයිස් එකකින් difference වඩා. Okay now. Right. Now I have a chance. Here x to the power p minus a to the power p is there. Now I have a chance of using this assumption. So I can this thing. Before that, I'll write another step. From this, you see that a to the power p is common to these two terms. You can take it out. A to the power p can be taken out. So that will give x minus a. When you take a to the power p out, that will give x minus a. Right? Now we have a chance. Now we have a chance of replacing this. What we created is this x here. Now we can replace it by x minus a into dx. That's getting some use of this assumption. Okay. So this is equal to, this can be replaced by this assumption, x minus a into dx, plus again we have a to the power p into x minus a. This I wrote substituting from this. Substituting by 2. Right? Now if you look at this again, you see that x minus a is everywhere. X minus a is everywhere. So we wanted to show that this is divisible by x minus a. Now you see that once you substitute from this, x minus a is everywhere. So we can take x minus a out. X minus a out from everything. Taking x minus a out. So that gives x into dx plus a to the power p. Right? So it's like x minus a into some portion, but no remainder. So this clearly shows that x minus a is a factor of this when n equals p plus 1. So this is divisible by x minus a. This is, that's what we have to show. We wanted to show divisible by x minus a. Therefore, you can say if this statement is true for n equals p, if it is true for n equals p, some integer, then it has to be true for n equals p plus 1 also. That's what we have proven in this step. Therefore, if a is true for n equals p, some positive integer, then it is true for n equals p plus 1 also. Right? Like we have done the main part of the proof. අර හැමදාම ඕකට පස්සේ පොඩි හැල්ලක් තියෙනවා ළමයි ඒකත් ලියන්න ඕන. To get full mark, you get 5 marks for writing like finalizing things. And මේ statement එක ලියන්න හැමදාම ඕන වෙලාවක මේ ගණනක් ඇදුවාම. Say this is number 3. Here we have said that if true for n equals p, then it has to be true for n equals p plus 1 also. By 1 we have it is true for n equals 1. මේ දෙක එකතු කරාම we can like complete the proof. මෙන්න මේක මතකද ලියන්න by 1 and 3. True for n equals 1, then 3 says if true for p, then it has to be true for p plus 1 also. By 1 and 3 and by the principle of mathematical induction, you can say this a is true for all n belongs n. So that completes the proof. all n belongs n, right? ඔන්න first example එක. ඔක දැන් තේරුණාද ළමයි? තව එකක් දෙයක් කරනකොට තව අදහසක් එයි. දැනට අන්තිම පේලිය පැහැදිලි නැනේ මං ආයෙ ලියන්න. ඉඩ තියෙනවනේ තව ටිකක්. කවන්නේ දැන් තේරුණාද ළමයි? පොඩ්ඩක් හරි තේරුණාද ඔය ප්‍රූෆ් එක පළවෙනියට කරපු එක්සැම්පල් එක? මොකද කියන්නේ ඔලිනා? කවිෂා? තව එක්සැම්පල් දෙයක් කරනකොට ඔයගොල්ලන්ට තව ටිකක් තේරෙයි. දැනට පොඩි අදහසක් ආවද? You got some idea of what this is? Olina says yes. What about the others? ඊළඟ ගාන හදනකොට මම ඕගොල්ලන්ට දෙන්නම් ඊළඟ එක. තව පොඩ්ඩක් තේරෙයි. ආයෙත් අය මොකද කියන්නේ? කවිෂා මොකද කියන්නේ? අභීත කවිෂා තේරුණා කියනවා. හරි. මට හොඳටම තේරෙන්න ඕනේ නැහැ පොඩි අදහසක් ගත්ත නම් ඇති. Okay. Linara, okay, thank you. Then take it down, right? Take it down. I can give the second question for you, right? Second sum. Hari, ikmanin liya gannako. Api ඊට පස්සේ බලමු. Liya ganna mai. Shall I write the second example and leave it for you? Question number 2. මේ දෙවෙනි එක්සැම්පල් එක කරාම ඔයගොල්ලන්ට කිසි ප්‍රශ්නයක් නැහැ. ඔබටම තේරෙයි. So the second example is 2 that 8 to the power n minus 3 to the power n is divisible by 5 for all n belongs to n equals 1, 2, 3, 4, 5 all positive integers n. හරි ඕකල තමයි මම ටිකක් කරලා දෙන්නම්. කරගෙන යන්න ළමයි. මේක කරගෙන යන්නකෝ. මම විනාඩි 5ක් දෙන්න කරගෙන යන්න. Right now. This time we are dividing a number by another number, right? So you will write that this is equal to 5 times some polynomial. We are not dividing two polynomials, right? We are dividing a number by another number. Therefore, this should be equal to 5 times, say, some r, for some r, a positive integer. For some, the assumption is this is equal to 5 into not the polynomial gx, it has to be some positive integer number. For some r belongs n. Now n equals p plus 1. Xn minus a, sorry, a to the power n minus v to the power n equals a to the power p plus 1 minus v to the power p plus 1. We want to create a to the power p, a to the power p minus v to the power p here. Relate that to balance 8 terms. I write 8. This is unwanted. To get rid of that, I will write plus 8 times 3 to the power p, then to balance minus 3 to the power p plus 1. This I will simplify. You can take 3 to the power p out. That will be 8 minus 3. Now I can use the assumption there. Assumption in this and replace this by 5r plus 3 to the power p. This is equal to 5. So 5 can be taken out. We want to show that it's divisible by 5. So 5 is common. You can take it out. W 8r plus 3 to the power p. So clearly it is this is divisible by 5. ඊට පස්සේ අර හැල ලියන්න ඕන මතකයිද හැම ගානකම අන්තිමට ඒ හැල ලියන්න ඕන ඒකට ලකුණු පහක් දෙන්න. Therefore if මෙන්න මේ ටික ලියන්න ඕන කඩපාඩමින් හරි. It is 2 4 some p n equals p belongs to n then it is 2 4 n equals p plus 1 also. It's number 3. So by ultimately ඉවර කරන්න මේකත් ලියන්න by 1 and 3 and by the principle of mathematical induction. A is 2 4 all n belongs n. That completes the proof. බලන්න මම මොනවද අඩුපාඩු තියෙනවා නම් හදාගන්න. ඔයගොල්ලන්ට තේරෙන්නේ නැති දෙයක් තියෙනවා නම් අහන්න. මේක මම හිතන්නේ ලේසි එක්සැම්පල් එකක්. Okay, can we go to the next example? Before going to the next example, I have to give you something. For the next example, you need some expansion. Expansion අපි binomial expansion කරලා නැහැ නේ ළමයි. Binomial expansion කරා නම් මම මේ කියන එක දෙන්න ඕනේ වෙන්නේ නැහැ. Binomial expansion එක තාම කරලා නැති නිසා ඕගොල්ලන්ට දැන්ට කරන්න පුළුවන් මෙතන එකක් මම දෙන්නම් මේ Pascal triangle, right? Pascal triangle, that's something you must have heard in O levels also. I'll just remind it. and see how to use it. And you don't need that when we do the more advanced method, binomial expansion later on. For the moment, use this Pascal triangle in this particular problem, right? Right. This is Pascal triangle. මේ පොතේ පිටිපස්සේ ලියාගන්න. මේ පාඩමට අදාළ නැහැ, right? පොතේ පිටිපස්සේ ලියාගන්න. Something not relevant to this lesson, mathematical induction. I think Pascal triangle is something we have heard in all of us. Let's see if you remember, even though not, I'll explain it fully. And that's Pascal triangle. පොතේ පිටිපස්සේ ලියාගන්න. And this is how you construct the Pascal triangle. You start by writing 1 and 1. 1 and 1. That's taken in the first line. First line consists of 1 and 1, right? Then the next line. We are going to the next line, next stage. Each stage starts by 1. Next stage starts by 1. Then in the middle of these two, you write the addition of them. 1 and 1, it is 2. And then end the line at 1, right? Starting and ending by 1. Then you go to the third, if you want to go to the third line, so that's also will be started by 1. Then in the middle of these two, you write the addition of them, 1 and 2, that's 3. In the middle of these two, you write the addition of them, that's also 3. Then the line is ended by 1. Similarly, you can go to the fourth step, fourth line, that will also be started by 1. Then in the middle of these two, 4. In the middle of these two, 6. In the middle of these two, 4 and 1. Right? Similarly, the next line. I'll write few more. Here it is 5, here it is 10, again 10, and 5 and 1. Go to another line. 1, 6, 15, 20, 15, 6 and 1. One more line. For the moment, I'll write one more line. 1, 7, 21, 35, 35, 21, 7 and 1. So this is Pascal triangle. And what is the use of this? Pascal triangle is used to find the expansion. A plus b to the power 3. A plus b to the power 3. This is something you remember by heart, right? Expansion is a cube plus 3a squared b plus 3ab squared plus b cube. This is the expansion. A cube plus 3a squared b plus 3ab squared plus 1. So these coefficients, 1 here, the coefficient is 1, right? Here the coefficient is 1, here it is 3, here it is 3, and again it's 1. These coefficients, do you see that? The first line, second line, third line. The third step gives these coefficients 1, 3, 3, 1. You can find these coefficients of the expansion by the Pascal triangle. Third line gives coefficient of the expansion of 3. The fifth line gives coefficients of expansion of 5. A to the power 5, if we want to write a plus b to the power 5, it starts as a to the power 5. The next term, a to the power 5 with b, sorry, a to the power 4. This reduces by 1. No b here, b to the power 0, then b to the power 1. Next term, a to the power 3, b squared. This is reduced by 1 and this is increased by 1. Then a squared b cube. A squared b cube. This is reduced by 1, this is increased by 1. Similarly, The next term is a b to the power 4 and finally b to the power 5. Right? The question is, what are the coefficients here? Coefficients. These coefficients are given by the fifth line. 1, 2, 3, 4, 5. Fifth line. Right? Fifth line. 1, 5, 10, 10, 5, 1. Those are the coefficients. 1, 5, 10, 10, 5 and 1. So you can use Pascal triangle to find the coefficients of these expansions. A plus b to the power n. ඕක තමයි මේකේ ප්‍රයෝජනය, right? But you don't need to know, you don't use this Pascal triangle once you learn binomial expansion, right? It's a more advanced way of finding this. දැන් මේක ලියාගන්න පොතේ පිටිපස්සේ මම ඊළඟට දෙන ගාන හදන්න ඔයගොල්ලන්ට ඕන වෙයි. මම ගානක් ලියලා මේ පැත්තේ. Example number 3. මේක ටක් කරලා ලියාගෙන ගාන හදාගෙන යන්න. අවශ්‍ය වෙලාවට මේක පාවිච්චි කරන්න. right මේක ලියාගන්න මේ ගාන හදාගෙන යන්න මම විනාඩි 5ක් දෙන්නම් කරගෙන යන්න හැමෝම තමයි මේක වෙනස් වෙන්න ඕනේ මම ඉස්සර ඉන්නේ n to the power 7 sorry it has to be n to the power 7 නා මම ඉස්සරලා ගියේ ඒකනේ sample එක ඉස්සරලා ඉස්සර දැන් වැරදිලා n to the power 7 right ඒක හදාගන්න very sorry n to the power 7 it has to be n to the power 7 please correct it when n equals 1 you get just 0 this is equal to 0 0 can be divided by anything but not 0 right anything except for 0 so this is true this can be divided by 7 therefore it is true for n equals 1 And now we want to create this p to the power 7 minus p here in this n equals p plus 1 part, p to the power 7 minus p. To create that, you will have to expand this to the power 7. It is to expand this, I gave you Pascal triangle. Use Pascal triangle to expand this. Hmm? Using Pascal triangle, expand it. So you get balance කරගෙන යනකො මම පොඩ්ඩක් වෙලා ගන්න. Right. Once you write this, the first thing you see is what one gets cancelled. One gets cancelled, and we wanted to create b to the power 7 minus p. Right? So these terms are there here. 3 to the power 7 maybe minus p. Maybe those two terms are there. So we can easily create it here and take it separately. Take them p to the power 7 minus p. That's what we wanted. And look at the rest of the terms. You see that we want to show that it's divisible by 7, right? For the rest of the terms, very easily, 7 is common. You see that 7 is common. So we can take 7 out. So that will give p to the power 6 plus 3 p to the power 5 plus 5p to the power 4 plus 5p to the power 3 plus 3p square plus p. You can take 7 out of all the other terms. Right. Now we have the chance of replacing this by our assumption. So this is equal to 7r by our assumption. Plus then 7 is common to all these. P to the power 6 plus shall I write some k for this? Adding all this p is some positive integer, right? So adding all this, you get some another positive integer. I'll name it some k, 7k, right? Where k is again some positive integer. This is substituting by 2. This is replaced by 7r plus 7 into all this I took as k for some positive integer k, right? So now clearly this is, if you want you can take 7 out and say this is divisible by 7. So r plus k is some positive integer. This is divisible by divisible by 7. Therefore, therefore, if a is true for it's true for n equals p, we have shown that it is true for n equals p plus 1 also. Main part is over. Now I will write the rest. N equals p, then what is clear than then we can go to the next example. එකක් කරමු ළමයි අද ඉවර කරන්න කලින් ටිකක් වෙනස් විදිහේ ප්‍රශ්නයක්. We have done 3 examples. All 3 are somewhat similar. In all 3 we have proven that this is divisible by 8 or 5 or this is divisible by that type of problems we have taken so far. Now a different one. Right, a different type of problems. An example, how to use. Sometimes they give questions like this, right? Sequences to prove some statement for a sequence. I'll explain it with an example. This example. හරි ඔක ලියා ගන්නකො ළමයි ඊට පස්සේ අපි බලමු කොහොමද කරන්නේ කියලා. Just take it down and then try to figure out the question. මේ example එක මාත් එක කරමු. So these are data. X1 equals 1. Xn minus 1 is equal to 1 plus n minus 1 beta. So that's what given about the sequence, right? Sequence is x1, x2, x3, x4, and so on. The sequence is defined by this. So this is what you have to prove. Xn equals n over 2, 2 plus n minus 1 beta. That's what we have to prove by induction, right? අපි පටන් ගමුකෝ වැඩි. These are data. X1 equals 1. Xn minus 1 equals 1 plus n minus 1 beta. So these are data. Right. To prove or proof of Xn equals, this is what we have to prove, n over 2, 2 plus n minus 1 beta. This is what we have to prove by induction, right? The first step is to prove that it is true for n equals 1. This is what we have to prove. When n equals 1, this gives x1 equals by a. By a you get x1 equals, when n equals 1, it is half 2 plus, when n equals 1, this is 0, right? 0. So it's equal to 1. x1 equals 1. And given also as data, in data you see that x1 equals 1, it's given, right? So therefore, this is true. This is true when n equals 1. This gives x1 equals 1. Again, you are given x1 equals 1. Therefore, this is true for n equals 1. Therefore, A is true for n equals 1. Right? Okay. Second step, when n equals p, suppose that A is true for n equals p for some positive integer p. Alright? Then the assumption gives that xp equals, you can replace n by p, that also n equals p. So this is what we have to prove. So when we assume that this is true for n equals p, so you get you can replace n by p. P equals p over 2 into 2 plus p minus 1 beta. We get this by assumption, right? Now we have to use this and prove that this is true for n equals p plus 1 also, right? So now the task is to show that this is valid for n equals p plus 1. ඒක හොඳයි පැත්තකින් ලියාගන්න එක. What you need to show in a case like this, it's better you write it down by the side. We want to show that x p plus 1 equals, when n equals p plus 1, p plus 1 over 2, 2 plus, when n is p plus 1, 1 get cancelled, you get 2 plus p beta. So this is the task, right? This is what we have to show. It's p plus 1 equals p plus 1 over 2, 2 plus p beta. It's p plus 1 equals p plus 1 over 2, 2 plus p beta. That's what we have to prove. Using this, right? Using this, getting some use of this, you have to show that x p plus 1 equals p plus 1 over 2, 2 plus p beta. That's the task. Okay. Now how to connect? Now how to use this to find something for p plus 1, x p plus 1. Kiyan බලන්න අදහස? මේකෙන් වැඩක් ගන්න කොහොමද? To show that it is true for n equals p plus 1. කොහොමද ළමයි මේකෙන් ප්‍රයෝජනයක් ගන්නෙ? කොහොමද මේක සම්බන්ධ කරගන්නේ? How to connect this assumption to prove this expression to get something for xp plus 1. අදහසක් කියන්න බලන්න. අපි මේ පන්තියේ පැය දෙකමාරක් විතර කරනවා ළමයි. මේක අනිවාර්යයෙන්ම අද හදමු. ඊට පස්සේ පැය දෙකමාරක් කරනවා. ඔයගොල්ලන්ට විභාගේ තව අවුරුද්දක්වත් නැහැනේ. Anybody give some idea how to use this, how to connect this with xp plus 1? අදහසක් නැද්ද කවුරුවත්? How to express xp plus 1 using xp? ඒ බලන්න මේ data එකක් දීලා තියෙන එකට තමයි you are given a relation between xn and xn minus 1, right? So just replace n by p plus 1. You get some relation between xp plus 1 and xp. Using this, you can express xp plus 1 in xp. Just replace n by p plus 1 in this expression. Like here now, given xn minus 1 equals 1 plus n minus 1 beta. So replace n by, or substituting n equals p plus 1, you get xp plus 1 minus xp equals 1 plus p beta. Now from this you can express xp plus 1 in xp. Just take this to the other side. xp plus 1 plus p beta, right? Now we have a chance of using our assumption here. Make again a method of an right? So replace this by our assumption. So it's p by 2 plus p minus 1 beta plus further we have 1 plus p beta. Alright. Now this is what we have to show. This is what we have to obtain. This is what we have to obtain from this p plus 1 over 2 plus p beta. Make a simplify කරන්න විතරයි තියෙන්නේ. We need divided by 2. I'll take half out. අපිට ඕනේ divided by 2 and take this in. That'll give 2p plus make a very grammar on p square beta. That's p square beta minus p beta. Make a taking it on plus 2 plus 2p beta. That's what you get taking half out, right? And here we notice that minus p beta plus 2 beta get cancelled. We need a p plus 1. P plus 1 taking 2 out, you get p plus 1. The two terms again p beta. It looks like half. Taking 2 out of these, you get p plus 1. And from the other two terms, we can take p beta. That'll give p plus 1. Now p plus 1 is common, you can take it out. Make a non p plus 1 over 2. You can take p plus 1 out, that will give p plus 1 over 2. Plus p beta. Therefore, you can say if it is true for n equals p, if this is true for n equals p, then it has to be true for n equals p plus 1 also. Therefore, if a is true for n equals p belongs n, then it is For proof by induction to be true, is it necessary for n equals 1? Oh, n equals 1 true එන්නම ඕනේ. එහෙම නැත්නම් ඒගොල්ලෝ කිව්වොත් that you have to prove that it is true for n equals 2 from 2 2 3 4 5 කියලා පටන් ගන්න එකට true වෙන්න ඕනේ. නැත්නම් අපි මේ කරන එකෙන් වැඩක් නැහැනේ. We prove that if it is true for p, then it is true for p plus 1. මේක අරගෙන ගිහින් දාන්නේ for the first step. For the first step, the proof of it is true for n equals 1. මේ chain එක පටන් ගන්න එතනින් n equals 1. මොකක් හරි පටන් ගන්න තැනට true වෙන්නම ඕනේ. නැත්නම් මේකෙන් වැඩක් නැහැ. ළමයි මේකෙන් ප්‍රයෝජනයක් වෙන්න you have to show that it is true for n equals 1. එතකොට මෙතනින් පටන් ගන්න තමයි chain එක යන්නේ. If true for 1, from this you can say then it is true for 2. If true for 2, then again from this it is true for 3. If true for 3, then from this again true for 4. මේ first step එක තියෙන්න ඕනේ. ඒක තමයි මේකත් එක්ක අපි සම්බන්ධ කරගන්නේ. Right? Whatever the starting value 1 or 2 or maybe 10, you have to show that it is true for that starting value, whatever the starting value, right? මේක ලියා ගන්න නැති නේ ළමයි. නිකන් හරි අඩුපාඩු තියෙනවා නම් ආපස්සට ඇදලා හරි ලියා ගන්න පුළුවන් නේ. අපි එහෙනම් පන්ති උතනින් ඉවර කරමුද අද? අපි මේ කරේ two types of applications or problems. We have taken two types of problems of proof by induction. There are two more. We'll take next day. Those two. The other types of problems in proof by induction we'll take next day. For the moment, for these, you have some homework. I'll post the tute, right? For homework, you have to do in the tute. Homework from the tute. Try questions from 1 to 4. 1 2 3 4, right? The tutorial 1 2 3 4. Metik kalla diyan lamai mam tute එක දාන්න තව ටිකකින්. Homework tutorial questions 1 to 4. Metik kalla diyan lamai එහෙනම් අපි අදට උතනින් නවත්තමු. ඔයගොල්ලෝ හැමෝටම බුදු සරණයි ආයුබෝවන් සුබ රාත්‍රියක් ප්‍රාර්ථනා කරනවා. හැමෝම ප්‍රවේශමෙන් ඉන්න. ඇවිදින්න යන්න එපා, එහෙම යන්න එපා. රටේ තත්ත්වය හොඳ නැහැ. ගෙවල් වලට වෙලා ඉතිරි සති දෙක තුන ප්‍රවේශම් වෙලා ඉන්න ළමයි. එහෙනම් අපි ඔතනින් නවත්තමු. බුදු සරණයි. Mm-hmm.